Good morning. I hope I'm not late for answering your question. But yeah, let's start. You were asking about the critical angle, and let's start with thinking about refraction first. So here we have the boundary, which is the surface of whatever something. Like here we have air and water. So this is the surface of the water. Well, another way of saying the boundary between the two different mediums. The medium one, which is air, medium two, which is water. And those two are different. Now, the word different, it can means a lot of things. Which one, يعني, we're talking about what kind of classification, right? Those two, in class, I say that they're different in mass, but there are other things that they are different at, which one of them is something called optical density. It is almost the same, but not exactly. That's why I'm usually avoid to use the word optical. I don't want to confuse you, but the exact thing that they are, like, we are concerned about them being different at is their optical density, which is basically the ability of an object to slow or delay the movement or the transmission of light in it. So if a material or a matter so good at delaying the light, it means that it has a high density, and usually it is close to the real density. So here we have the air less dense than the water, and so it is better, or like it doesn't slow down the array of light when it comes through it. And so this will somehow affect the path of light. And when we're talking about the path of light changing the medium, going from one medium to another, we're talking about refraction. And so again, this is the boundary or the surface. And here we have our like ray falling into this point. How can we find the angle of incidence? We have to draw the normal, and this is our normal. I is the angle of incidence, which is trapped between the normal and the ray of incidence. Yeah. So here, air is less optically dense than the water, and so the ray is it is traveling from less dense to more dense, which means that it's going to be slowing. Instead of going this way, now it is a little bit slow and going this way. And this is our R, right? I hope it's clear up to this point. And now, what if the light is coming from the water, then going to the air, which means that from the high dense medium to the low dense medium. Again, we have our boundary here, and let's draw the normal from now. And here we have medium number 2, or medium. Did I just write water in the wrong way? I did. Let's erase it. Water, and this is air. As long as they are different in optical density, right? So here we have the light coming from this point to here. I, which is the angle of incidence here, right? So getting from going or traveling from from the more or greater dense medium to the less dense means that the light is going to be going faster now, which means that it's going this way. Instead of going this way, it is too fast that the angle of refraction is going to be greater than the angle of incidence. Is it clear till now? So what if, now I know that the angle of refraction is going to be getting bigger and bigger since, this is a little bit ahead. So here until this point, I hope it's clear, the angle of incidence is I, for example, is 40, then the angle of refraction, since the light is traveling from from a denser or optically denser medium to an optically less dense medium, it's going to be, the light is going to be going faster, which means that the R, the angle of refraction, is going to be bigger, greater, right? It makes sense. Like, it is less crowded there, optically at least, and so the light will be able to run away from the normal. And here, if I made, like as I mentioned, if this is, let's say 50, this one has to be more than 50. R definitely is more than 50. Since we're going from water to air, from glass to air. Now, if it's the other way around, the angle of refraction is always going to be less than the angle of incidence. That's if we're going from a less dense to a more dense medium. But the critical angle and these kind of things only happen if we are at the slow medium or the more dense or the more optically dense medium to the less. So this is the more or the slow medium. This is the more dense. Tamam? Now let's try something else. If this one is 50, let's go with 60 now. What do you think the angle of refraction will be? Is it going to be more than before, more than this R, or less? Pretty much it's going to be more, because here, when the angle of incidence was 50, this one was greater than 50. So when it's 60, again, it's the same. We're going from water to air. So R has always to be bigger than I. And this is what's going to happen. The light is going to run away even faster, and then R is going to be greater. Now I want to make it even bigger. When I'm talking about the angle of incidence, I'm going to make it bigger. So this one is, I don't know, maybe, my drawing is so bad, but I think you get the point. So here it is, let's say 70. It's pretty much more than 70, but who cares? And this is going to be like this. Right? So R still bigger than I, which means that R is almost, you see, R is getting bigger. The bigger the I, the bigger the R, because R has always to be bigger than I. Since we're going from the slow medium to the faster medium. And let's get into another one here. And this is almost what? This is almost 90, so it is pretty much 80 something. And here, the refraction is going to be like this. R is so big, it's almost 90. So again, R has to be bigger than I. So R is getting closer to what? To 90. Here, let's go with this. When it is too big, let's say, it depends on the material, by the way, in the matter. So it is too big, like, I don't know, I, for example, is 85 for this exact material. Then here, you see this one is getting bigger, bigger, closer to the surface or the boundary. At some point, it will be on that boundary, parallel with it, like on it. So this is going to be R, which happened to be 90, right? So now R is bigger than I, but R happened to be 90. It is on, like it's, يعني, the greater the angle of incidence, the greater the angle of refraction. And so it will get to at one point when it is right on the top of the boundary itself. And so, okay, until this point we're fine. What do you think is going to happen next? Now this one is bigger than 50, well, this is 87, let's say. What's going to happen to the refraction? Now we got to 90 at 85. How can I, like, what's going to happen next? There's no place to go unless it is inside the water again, because here at this point we got to the boundary. Now what should we do? The only place for the path of light is to get inside the water again, and this is what's going to happen. That's where the total internal reflection happen. And this is where the angle of incidence is going to be the same as the angle of reflection. Now it's no more refraction. It's becoming reflection. Because it was getting bigger, bigger, bigger until at one point when it reached the boundary, and this is when the R is equal to 90, and now it is getting back to the same slow or high optical density material or medium. So this is why we have the total internal reflection. And when the transmission or the transformation from refraction to reflection, I don't know how to talk no more. Allah. When does that happen? It happened when the angle of incidence, I, was greater than, when the angle of incidence was something that caused the R on the other side to be greater than 90. So at this point, when the critical, when the R was, was 90, here, after this point, things started to change. Now, whenever, like, anything that is in the eye, anything that is greater than, let's say here, 85, is going to be totally internally reflected inside. So all of the things happened because of we somehow managed to find an angle of incidence that will reflect the light with an angle of refraction greater than 90. When it's 90, tamam, but when it's more than 90, so things are going to change and the light is going to be inside the slow medium again, and it's going to be reflection then. Since it's happening on the same medium, that's reflection. And reflection has its own rules and, principles and so on. So if you want to have a better term to call the eye, this eye that caused everything to happen, because it's kind of a special angle for each medium. Like any medium, they have their own critical angle. Yeah, so I'm saying this is I in this case is equal to the critical angle, which is the angle of incidence that will reflect the light, refract the light with an angle of refraction equal to 90. And after that, it's okay, let's say it is the angle of incidence in the slow medium or in the more dense medium that will cause the light to be refracted with an angle equal to 90%. And it is the angle where things will start to change from the normal refraction to the total internal reflection. So let's say like we have a medium that is the critical angle in that medium is equal to 38, and I here, the light from medium, from let's say, okay, glass, and here we have the air. So again, this is more dense than this. And I have the light to fall with angle of incidence equal to 40. What do you think the path of light is going to be like? Is it going to be refracted like this? No. It is going to be totally internal reflected like this, where I here and R here is R, both of them are equal to 40, because this is what's happening in reflection, right? So why did it, instead of going or escaping the glass and going to the water, to the air, what happened? Why it's reflected inside? Because the angle of incidence, I is equal to 40, happened to be greater than the critical angle, which is 38, which means that something less than 38 will cause the refraction to be on the boundary, which is 90, and then after that the transformation of from refraction to reflection is going to happen. I talked for so long, I hope it's clear, and I'm not taking a lot of your time. Please watch that if you get time, of course, with speed like 2 or so.